Hello, this is Darrell Berry Jr. back with some linear algebra, and I'll be doing some more of the reading and working through the solving an inconsistent system, which is an interesting process or idea. So we'll continue where we left off. Right now I'm working an example in the book, and what I'll do is basically show how this is the case, and that would allow me to double check the project. Those who listened earlier know I was working on a project earlier. I think I did it successfully and submitted it. So, but we're going to make sure that I have all the details right. So putting some extra attention, because I know I didn't put as much attention as I could have, I think, on the previous exam. So I want to make sure that ace the next two. So we'll see how that works. So this is where we were. And we left off with theorem 2.5 in chapter 3. And it says the column space, which we know are the vectors of the matrix, which span the subspace. So just taking the vectors of the matrix in question, and they span that space because that's where we get the matrix from. Perpendicular to that equals the null space of the transverse of a matrix. Right? So we're saying that the column space of A, the vectors that span that subspace, if you take the matrix A and transpose it, and then solve for the homogeneous system, that will equal, or that will be in the same space as the transpose of the column space of A. All right. So check the video, the one I did earlier about column spaces and null spaces if you're not clear on that. So now we can say AX, I'm still not sure why there's a bar over the X, equals P. I guess it's because that X is P minus P. I'm not sure why the bar is there. And A transpose B minus P equals 0. So A transpose times the yellow line, which is B minus P, is 0. I'm thinking about this here. That's when we get to the examples, it'll make more sense. I found it easier just working the problem and understanding all the concepts behind it. Substituting the first equation into the second equation yields A transpose B minus A x bar equals 0. A transpose B minus A x bar equals 0. I forgot to distribute my AT onto this one. So that means that A transpose times B equals A transpose times A X bar. Okay. So we can say that A transpose A is the inconsistent. So we'll say that X bar means is an inconsistent system, which means there's no solution, equals the same transpose times B. So the transpose of A times B, that must equal P. So this plane right here is AX equals P, or if I'm understanding this correctly. So A transpose times B, I'm not sure. We'll keep going. But this seems clear enough. We can't solve for X directly because there's no solution, but perhaps we can take the transpose of A and multiply it by both sides. And now I'll end up with a different matrix. I'll call it B, X bar equals something different here. We'll call it P. I'm not sure if that's the best way to write that. So let's see how they write it. But this is the equation we were looking for. We already know this equation has at least a solution because P exists. Okay. That makes sense. Because we combine those two together, and P, if we plug P in, these AX, AT is going to equal ATP because P is one of the solutions. Is that what I wrote? ATAX equals ATP equals ATB. Since by construction, the rank of A is n, we claim that ATA is non-singular. And let me remind myself of the definitions of singular, non-singular. An n by n matrix of rank equals n is called non-singular. An n by n matrix of rank less than n is called singular. And this is the page I'm looking at and thinking over here. in my n matrix, r equals n is non-singular, r less than n is singular. So if it has less pivots than it has columns, then it's singular. If it's the pivots, so non-singular means there's a pivot in each row, hence in each column of its echelon form. Thus, its reduced echelon form must be the n by n matrix. So the unique solution means non-singular, which I think is a contradiction. Shouldn't it be singular if it has a unique solution? So unique solution is non-singular. If I'm understanding that correctly. Let's go back to where we were. Right? So it says suppose X is in the null space of A, T, A. So this means that X is a solution to A, T, A, X equals 0. That's what that means. If X is in the null space of that, that means ATAX equals 0. Which they say on the next page. So ATXA equals ATAX. Right, so I think I'm understanding this. So dotting with X, we get ATAX dot X equals. So when I bring this A transpose across the dot product, it becomes A not transpose in order for them to be equal. So that equals the magnitude of X. So I'm gonna make a video about just proofs one day, or just go through proving this stuff. So I'll make a note. But I know it's gonna take some time. It's gonna be a video in itself, but I'll make a note of it. Therefore, AX equals 0. Because the magnitude of AX equals 0. That makes sense. Since A has rank n, we conclude that X equals 0. So thus AX equals 0, and A, since rank of A equals N, X equals 0. As a result, we have the following definition. Definitions are good. Definition. Given A is M by N, rank of A equals N, so there's a pivot on every row column. The least square solution of the equation AX equals B is unique solution of the normal equations AT A X unsolvable equals AT B. Right, so we mark on the definition. When rank A, I guess they always spell out right. When rank A is less than N, there's less pivots than the number of columns. The normal equations are still consistent, but have infinitely many solutions. Every one of those solutions, X, gives rise to the same projection, AX equals P, because P is the unique vector in the column space of A. With the property that B minus P is in the null space of the perpendicular of A. Right? So I'm gonna copy this illustration down. Right? So B minus P, which is the yellow line, is in the null space of the transpose of A. So the null space of the transpose of A means the solution AT X equals 0, X solves this. X is in the null space of AT. So X is in the null space of AT, A transpose, plus ATX equals 0. And it's saying that, oh, so B minus P is the yellow line, is in the null space of A transpose, because A transpose times B minus P is 0. that the A transpose is perpendicular to AT. The AT is the vertical from the subspace. Column space of A, the transpose of column space of A is the null space of A transpose. Right. Looking at this page here, thinking the null space of A transpose is the vectors that times A transpose equals 0. Okay, so the column space of A transpose comes out the page, and the null space of A transpose means it's the vectors times A transpose that equals 0. Well, see, it's not a dot product, it's times that, so it's coming slightly more clear. The main thing seems to be remembering this formula right here. AT AX equals ATB, the transpose of A times both sides when we have an equation we can't solve. B minus P is in the null space of the transpose of A. We define the least square solution to be the unique vector. X is in the row space of A that satisfies the normal equations. Of all the solutions, this is the one. This is the one of least length. This leads to the pseudo inverse that is important in numerical analysis. See Strang's book for more detail. Summarizing, we have proved the following proposition. Suppose V is a subspace of Rm. V is in Rn, but it's a subspace of Rm. Those basis vectors that span the subspace. And let A be an m by n matrix. So you can say span V equals V1, Vn, and let A be the m by n matrix, whose columns are the basis vectors, are these basis vectors. So A, m by n, and the columns that span this subspace are the columns of A, as we discussed earlier, whose columns are the basis vectors. Given a vector B and Rm, the projection of B onto the vector space, which is P, is obtained by multiplying the unique solution of the normal equation by the matrix A. The projection of B onto the vector subspace to its subspace V is obtained by multiplying the unique solution of the normal equations via the matrix A. So P equals the projection onto V of B, which we discussed earlier. P is the projection of B onto the subspace V, which equals A x bar has no solution. I don't see how. Guess I'm still not getting the A x bar part. What that equals so A equals A A inverse AT. All right, now he's doing too much. All right, let's do an example. Maybe that'll clear some things up. Example 1. To solve the problem we posed at the beginning of this section, we wish to find the least square solution of the system AX equals B. And it's the same numbers from before, so I'll copy those. So we have A equals 2, 1, 0, 1, 1, 1, 1, negative 1, B equals 2, 1, 1, negative 1. And did I try to do row operations on this? No. I just got the column space and the null space. So we need only solve the normal equations. To solve this, A transpose A x equals A transpose B, which means we have 2, 1, 0, 1, 1, 1, 1, negative 1, 2, 1, 0, 1, 1, 1, 1, negative 1, x equals 2, 1, 0, 1, 1, 1, 1, negative 1, 2, 1, 1, negative 1. All right? That's why we have to transpose it so it can actually work with B. Now we have a 2 by 4 and a 4 by 1, and a 2 by 4 and a 4 by 2. So we'll multiply these out and say, so this is going to end up being 2 by 4, 4 by 2. So this is going to end up being a 2 by 2. So we have 4 plus 1 plus 1, 2 plus 1 minus 1, 2 plus 1 minus 1, 1 plus 1 plus 1 plus 1. X equals, so this is a 2 by 4 and a 4 by 1. So this is going to end up being a 2 by 1. See my previous videos to see why if you're not clear on that. So we have 4 plus 1 minus 1, and 2 plus 1 plus 1 plus 1. So that's going to equal 6, 2, 2, 4, x equals 4, 5. So as expected, this is a 2 by 2 and a 2 by 1. So now we should be able to solve this. So I have, yep, looks like I'm in the right direction. So we have 6, 2, 2, 4, 4, 5. So that's going to equal, let us do thinking the best way to do this with less fractions or whatever, but maybe there's no best way. I would just say minus 3 row 2 plus row 1 is row 1. So we'll say minus 3. So 0 minus 3, negative 12, negative 10, and minus 3, negative 15, negative 11, 2, 4, 5, and then we'll do things, and I have a solution. Oh no, I looked at it incorrectly. I think. So why don't we do I'll divide row 2 divided by 2. So that'll give me 0, negative 10. Now multiply that by negative 1. 0, 10, 11. And we have this divided by 2. So this is 1, 2, 5 over 2. Right? So 10x2 equals 11, and x1 plus 2x2 equals 5 over 2. So x2 equals 11 over 10. So that means that x1 plus 2, 11 over 10, equals x1 plus 22 over 10 equals 5 over 2. So that means that x1 minus 25 equals 25 over 10 minus 22 over 10 equals 3 over 10. So that means x equals 3 over 10 and 11 over 10, which is the closest we can get to solving for B. So let's see if that gives me an answer. Look, so that equals 1/10, 311, right? So using the formula for the inverse of a 2 by 2 matrix, for example, 4 on page 105, we find that x bar, so this is x bar, the solution for the unsolvable, is AT. Oh, so they brought this to the other side and said x bar equals, so this is the crazy thing they had, ATA -1 ATB. It's interesting. There's many ways to look at things. Choose a different color here. So when you bring the matrix to the other side, it stays to the left or to the right, but it becomes a inverse. Awesome. It's the least squares solution. Remember, while we're at it, we can find a projection of B onto the column space of A by calculating AX or AX bar, since now we have the X bar solution. So as an extra, the projection of B onto the column space of A equals A X bar. So still fuzzy on a few details, but I'm more clear. And I think I confirmed that I did the problems correctly. So I'll go ahead and stop here for now. And remember that you can sign up for tutoring. You can sign up for X, a Patreon to support. Join my Discord. We can have some conversations there. And what I'll do is come back, if not tomorrow, sometimes during next week. And we'll continue going through the book, doing some examples. And then I'll actually work some homework problems as well from the book, from the back of the book. Not the back of the book, but the back of the chapters and so on and so forth. So thanks for joining. Like, subscribe if you haven't already. Let me know in the comments if you have any questions on anything. And I'll see you all next week. If not tomorrow, by let's say Tuesday, I'll be back.